already, and they've been very nice. And I'll try to tell you a few things about the same subject that will address, fortunately, as it turns out, slightly different issues, though there'll be a few overlaps. And the work I'm going to describe here is based on these 4 papers. 3 of them are with Kostis Papageorgiakis, who's a postdoc at Tata Institute. The third one also with Bobby Erutachan, who's also a postdoc there, and both of them are present here. This one with Jacques and Mark as well. And there's a new paper with Mohsin Ali Shahiha, which is to appear. And actually it will partially address Steve Gubser's question on higher order corrections. Okay, so I'll start with the motivation and background. So my view is that we understand the field theory on multiple D branes very well. I think most people would agree. And the one on multiple M2 branes not so well. And I still think that we should hope to understand it better. Now this is roughly what Neil was talking about. In string theory, the first diagram indicates the interaction between 2 parallel branes, let's say D2 branes, but that turns into one continuous hyperbolic looking thing in M theory, and this kind of difference should somehow appear from our theory, and I think it's still a somewhat distant goal, although the triangle law that Neil mentioned is probably one of the interesting directions. Now there's an in-principle obstacle for writing an M5 brane field theory with all symmetries, because the M5 brane has anti-self dual 2 forms on it, but as far as we know there's no obstacle for writing a field theory on M2 branes, and yet until last year the point of view was that it can't be done, and this was an example, I think, of saying it can't be done because it hadn't been done, and now that it's been done with a certain amount of success, of course we all agree that it can be done with that amount of success, but I think it can be done better. So that's a prediction, and my point here is that despite a couple of 100 papers and 2 talks that we've just heard, I think it's fair to say that we are not exactly sure what the multiple membrane theory is. Now you know that in France there's an authority in charge of all branes, and even this authority doesn't quite seem to know the answer. Okay, good. Now there's one description of the M2 field theory that's clearly right by definition, and it's the one where you take Yang-Mills, scale out the Yang-Mills coupling to the front, and then put this limit sign in front of it. So that takes you to the infrared limit of the Yang-Mills theory on D2 branes. And although this description hasn't been very useful, it's obviously correct. So the question then is whether the fixed point described by this equation has an explicit Lagrangian description where all the symmetries are manifest. And in fact, as we've seen, all the symmetries cannot be made manifest to describe M2 branes just in flat space for getting orbifolds. The best you can have somehow is n equals 6. Among the symmetries, you'd like to have a global SO8 symmetry describing rotations of the space transverse to the membranes, enhanced from SO7 in super Yang-Mills. So that extra direction is the M direction and unifies with the other 7. So let me take a look and try to sort of classify together all the theories that you've already heard about. The first class are the Euclidean 3 algebra theories of Bagger, Lambert and Gustafsson, labeled by an integer k. The algebra, unfortunately, is stuck to be just one particular algebra, and in some description that's SU2 cross SU2. And as Neil has argued, it describes a pair of M2 branes at some kind of ZK singularity where k equals 2 is reasonably clear, and the other cases it's not exactly clear what the geometrical singularity is. And this can't be generalized to more than 2 branes. Now there's the Lorentzian 3 algebra, and somewhat to my own surprise, much of my talk, the second half, will be on this subject. And it was proposed by these first 2 groups, and in that form it appeared to have negative norm states, but there was a revised proposal, which is the one I'll be discussing exclusively in this talk, in which a certain symmetry was gauged, a certain shift symmetry was gauged, and that actually manifestly removes the negative norm states. Unfortunately, as it seemed, it removes many other good things about that theory, but I still think it's a very interesting theory, and I'd like to tell you about it. One good thing about that theory is that it definitely corresponds to D2 branes. The question is whether it's a useful description of M2 branes. And remarkably, it has all the symmetries that we want. And the last class, which you've heard of in much detail from Juan, is the ABJM and ABJ family. And in this case, you have a Chern-Simons structure with G cross G prime for special groups G and G prime, a family with integer k, but only n equals 6 superconformal invariants. It's a kind of three algebra theory. If you relax one of the fundamental assumptions for three algebras, which is complete antisymmetry of the structure constants. Now, again, it's obvious that this theory is correct, but it seems to be based on these orbifold singularities, and it's a special case when k is 1 that somehow it's the orbifold which is no orbifold at all. And that theory, instead of having all the symmetries we'd expect of free M2 branes in flat space, is missing two manifest supersymmetries, and also its center of mass mode is not manifestly a free field, although Juan argued that there's a composite field which appears to be free. Okay. Now, these theories all have 8 scalars and 8 fermions. They have non-dynamical Chern-Simons like gauge field couplings, and I'll try to classify them in this way. One set are the Euclidean signature 3 algebras. All of them, including the ABJM, have this different structure of Chern-Simons, 2 Chern-Simons actions. So Bagger, Lambert, Gustafsson is this group, ABJM are these groups, and then there are some other choices. And in these theories, the scalar fields and fermions are bifundamental. The Lorentzian signature 3 algebras have a slightly different structure. They are B wedge F theories where B is one gauge field and F is the field strength of another gauge field. Okay? And here, the scalars and fermions are a singlet labeled as xi plus, 8 of those, as well as an adjoint. So it's a somewhat different structure. But what's in common is that both classes make use of a triple product, and this you could argue just dimensionally, because if I want a classically conformal theory in 3 dimensions, a scalar field has dimension half. So the potential should be, if it's the square of something, then that thing should be cubic, so that the potential is sextic and scale invariant. And that's the case in both of these, but in different ways. Here you multiply bifundamental with its conjugate with a bifundamental, and then you take the mod squared of this and arrange these indices in various ways. In the second case, there's the singlet multiplying a commutator. Okay. The potential has this form in both cases. Okay. Now, one might have expected a simple and unique description for the theory on M2 branes in flat space-time. It's really the best analog in M theory of n equals 4 super Yang-Mills in type 2b. The excuse we have for not doing better than we've done is that the theory we're looking for will be strongly coupled. So in fact, even if you did have the classical action, you might ask, what does it mean? You need in some sense the full quantum effective action. But it's also got to be maximally superconformal, and we've seen in the previous 2 talks that satisfying all these constraints, it hasn't been possible to find the theory. So now I'll turn to a discussion of some things that we have understood about the various candidate theories, and I think they lead us in a certain direction, which hopefully will lead us to the final or correct description of M2 branes. Now, the following result holds true for all G cross G Chern-Simons theories in this class, that is both Bagger, Lambert and ABJM. And the statement is that if we give a wave to one component of the bifundamental fields, then at energies below this wave, the Lagrangian, which is a G cross G Chern-Simons Lagrangian, turns into a Yang-Mills Lagrangian with the wave squared appearing in front, plus corrections, higher order in the inverse wave. So just going on the moduli space makes one of the gauge fields, the diagonal gauge field of G cross G, into a dynamical gauge field. Now, that's rather surprising. That's not how Yang-Mills works. If I start with Yang-Mills and go on to the moduli space, I just get Yang-Mills for the subgroup of the original group. But here instead, Chern-Simons transmutes into Yang-Mills. So before trying to explain this, let me just give you a quick derivation. Here's the difference Chern-Simons action, and by taking the plus and minus combinations of these gauge fields, you can rewrite it in this form, and you see that it's actually a B wedge F theory with some corrections. the scalar, the covariant derivative, because x is bifundamental, has a on the left and a tilde multiplying it from the right. Now if I take a wave of x, the bifundamental x, say proportional to the identity, then this, the kinetic term for this, contains a mass term for the field A minus, but the field A minus is not dynamical. It's appearing there, it does appear in interactions, but it doesn't have a field strength of its own. So the mass term, along with this first term, simply can be used to eliminate A minus to leading order, and we get a Yang-Mills action for A plus. So this is the Higgs mechanism that gives us a dynamical Yang-Mills field starting from Chern-Simons fields just by going on the moduli space. Of course, there are corrections, and this is very important. Okay. Now one can check, in fact, that the bifundamental reduces to an adjoint and all of n equals 8 Yang-Mills assembles itself when you do this. But how are we supposed to physically interpret this equation? So it does seem from this equation that the M2 branes hypothetically described by this theory have turned into D2 branes with the right gauge group, because remember, this is typically something like SUN cross SUN or SU2 cross SU2, and this is a single SU2 or SUN, exactly as you'd expect from D2 branes. Okay, so it does seem like we are compactifying the theory, but of course it can't be, because we've just gone on the moduli space. And the answer is to this puzzle is that in fact there are these extra terms, and so for any finite value of v, of course there are all these terms, and so by going on moduli space we haven't only got Yang-Mills, we've got Yang-Mills with lots of corrections. Still interesting, it's like a reorganization of the theory, but it's not just Yang-Mills. There's one limit in which it is Yang-Mills, and that's when the wave goes to infinity, and that's when all these terms drop out and you have this result. Now what you see on the right side is by definition the theory of M2 branes. It's the limit as the coupling constant goes to infinity of the Yang-Mills Lagrangian. So we've shown that on the moduli space the original G cross G theories have one point for very large wave where they're actually equivalent to M2 branes. So we think of this as a proof that the original theories are the theories on M2 branes. Okay? So both sides of this equation represent the theory on M2 branes in different language. It's interesting that we showed this for the original Bagger-Lambert theory, but this also works for the ABJM theory, which on this side could have SUN cross SUN or UN cross UN. And then after going on the moduli space, you just get the Yang-Mills for the diagonal UN. Okay. Now, when you introduce the Chern-Simons level, then something quite different happens. And this was done in a subsequent paper. If you introduce the Chern-Simons level, whatever I did before was for k equals 1. Now you see k is present in every term of this equation, and it's possible to take a limit which decouples all the other terms from the first one, namely take k to infinity and v to infinity with the ratio v squared by k fixed. In that case, the right side actually reduces to this with G Yang-Mills defined by that equation, and this is definitely the Lagrangian for D2 branes. So in this case, somehow we have compactified the theory. There's no contradiction because we haven't just gone on the moduli space, but we've taken a correlated, we've taken a large wave and correlated it with taking a large value of k, which as we know is some kind of orbifold rank. So how can it be that by taking large k and large wave, we've compactified the theory? Well, this is an old observation due to a paper of Arkani Hamed, Mortal, Cohen, I forget the other authors, many years ago. And their point was that on orbifolds, you have this cone which becomes narrower as k, the degree of the group becomes larger. And if you pull d branes away from the orbifold point, at the same rate as you make k go to infinity or in a correlated way, then this cone turns into a cylinder, and then the cylinder has a finite radius, in this case square root of v squared by k. So actually in this limit, the M2 branes are effectively experiencing one compact direction, and therefore correctly they turn into D2 branes. Now in our paper, we observed that the orbifold C4 mod Zk. So we propose that the space-time description of this theory is the orbifold C4 mod Zk, the same one that later was discussed by ABJM. And we also pointed out that the orbifold has n equals 6 supersymmetry and SU4 R symmetry. We made one mistake. We were trying to match an n equals 8 supersymmetric field theory with a space-time description that seemed to have n equals 6. So we said, well, maybe for some mysterious reason the n equals 6 on the space-time is enhanced to n equals 8. The correct answer is the opposite. The space-time does have n equals 6, but the field theory we were discussing was the Bagger-Lambert-Gustavson original field theory. That has to be replaced by the n equals 6 field theory of ABJM, which clearly we didn't know. Nevertheless, this mechanism works as well in the ABJM case, and it is actually to date the only way to reduce these theories to D2 brane theories. One lesson we learned from all this is that for large K we are in the regime of weakly coupled string theory. Juan has emphasized this in his talk, and I want to emphasize that although that's very nice and it allows us to do many things in holography, but if we want to understand the basics of M2 branes, we want to be in the opposite limit. K should be 1, or there should be no K in the theory, and we should be in completely flat space and have some description of membranes. Okay. So in the second half of my talk, I'm going to talk about something that at first looked very promising, then later it didn't look so promising, and now I think it looks promising again. Okay, so what is it? So this is the Lorentzian 3 algebra theory. It's an extremely beautiful theory, and it has properties that should make us sit up and take notice. It's a B wedge F theory, I've told you. It has this covariant derivative involving both gauge fields A and B, but while A appears with a commutator, B multiplies a gauge singlet field of A. It has this structure of sextic interaction potential, and it has this extra term with an auxiliary gauge field C mu I, which if I integrate out, sets xi plus to a constant, and therefore allows me to pass to a description of the theory where x plus is simply equal to its own wave with no fluctuations. Now, these theories are a violation of a theorem that Juan told you earlier this afternoon. He said if someone gives me a strongly coupled action, I can put a parameter in front, and then it would be a weakly coupled theory. At worst, the parameter is quantized, but it can still have a limit where it's weakly coupled. Well, take this theory and put a parameter in front of it, and you'll find that you can rescale it out. It's crucial that it has this Lorentzian 3 algebra structure, so B and F can be scaled independently of each other, and if you follow through the procedure, you'll find that you can scale out any constant. So this is a constant free theory, and it has nothing to do with orbifolds or K or any large K limit. Okay. It also has manifest SO8 global symmetry because all the scalar fields and fermions, which I haven't written, have this index capital I going from 1 to 8, and it's obvious that they're rotationally invariant. So that's another good thing. And I've already said this, the equation of motion of C mu I implies that x plus I is constant. There's an I index missing. This is x plus I. Good. Now let's try our Higgs mechanism in these theories and ask what happens if you give x plus I a wave. Remember, it's a singlet field, and you find the very surprising result, not surprising in hindsight, but initially, as was pointed out, I believe, first by these people, that if you do that, then this 3 algebra theory reduces to Yang-Mills with no corrections. Okay? So the Higgs mechanism works, but it works a bit too well. And it leads one to suspect that the theory is a reformulation of super Yang-Mills in some form. Now, that is essentially true, and the next thing we did was to argue that you can start from n equals 8 super Yang-Mills and follow a systematic procedure involving a duality transform and derive this Lorentzian 3 algebra theory. Thank you. Now, this procedure borrows an old, not so old, but previously known duality due to Dewitt, Nicolai, and some Kleben, which works specifically in 2 plus 1 dimensions. And I think this duality, which is probably unknown outside the supergravity community and was certainly unknown to us until this time, is actually very interesting and deserves study for its own sake. So I'll describe it to you. So the idea of this duality is to take a Yang-Mills kinetic term, replace it by a B wedge F theory and an extra term. Now, if you look at this, you'll see that if everything was abelian, this is pretty much reminiscent of the usual duality in 2 + 1 dimensions, which replaces a gauge field by a dual scalar. But this has a few little extra twists. So let's just go through it. This is a gauge field strength F mu nu, which is non-abelian. And I want to emphasize that for this discussion, it can be in SUN. It doesn't even have to be in UN. So it doesn't have any U1 part. It can be completely traceless. So this is not doesn't reduce to the abelian case. This is a different case in a sense. Okay. So the first thing you have is the B wedge F like Chern-Simons interaction, where this F is the field strength of some other of the original field A. And then you have here a covariant derivative of a new scalar phi, and in that covariant derivative appears also the gauge field A, whose field strength is F. So what you see is that after performing this duality, the original gauge field, which was dynamical, has not disappeared from the theory as it should in a true duality. It's still there, but it's somehow being rendered harmless. It's harmless because it only appears in a Chern-Simons action and it appears in a covariant derivative, but no longer has a Yang-Mills kinetic term. Now notice that this action has a new symmetry. First of all, it has the old gauge symmetry under which phi and B both transform as adjoints. It also has a shift symmetry in which phi can be shifted by an arbitrary matrix, so it's an abelian symmetry, and B changes by this amount, and you see that this term is invariant, while in this term, when B shifts, you just partially integrate the D on F, and by Bianchi identity, that's 0. How do we know this duality is true from left to right of this thing? Well, it's easy to go back. Use this symmetry to set the field phi equals 0. Then you have B squared plus B wedge F, integrate out B, and you've got the left side. So the duality is obviously true. What good is it? Well, let's try to implement it in n equals 8 super Yang-Mills. The first line is the duality transform of the original Yang-Mills term. The other terms are just the terms that we already know in Yang-Mills. I've just written them down. But when we combine them, something interesting happens. We see that SO8 invariance starts to appear from a theory that was SO7 invariant. First of all, I'll rename this phi as X8. And second, I'll define the hatted covariant derivative as d mu xi minus a mu commutator xi minus g Yang-Mills I times b mu, where g Yang-Mills I is an 8 vector which is 0 in 7 components and g Yang-Mills in the last component. Then you see that this term is d hat mu of x8 squared, and these terms are just what they were before. B doesn't appear in them because g is 0 in those directions. But next we can allow g Yang-Mills I to be an arbitrary 8 vector because the action now has SO8 invariance if I also transform the coupling, and I can use that to bring the coupling to a form where it's all zeros and one non-zero component. Okay? And I want to emphasize that all that I am doing is perfectly justified and just giving you the same theory as the theory you had before. Now, the resulting theory can be written in this nice way where it looks SO8 invariant, but of course it's not, because the SO8 transformation should rotate not only the fields xi but also the coupling constants gi. Now that obviously isn't a symmetry as we understand it in field theory, it's just a symmetry of the formalism at best. But the last step is to say I'll replace this vector of coupling constants by a new scalar field on the condition that the new scalar field has an equation of motion which renders it constant. If that's the case, then of course I can do this, because then I can always treat that scalar field on shell as a constant. Okay? So I'm going to replace g Yang-Mills wherever I see it by this scalar field x plus I, and in this way, okay, I also have to add this Lagrangian, which is like a Lagrange multiplier setting x plus to be a constant. That was a condition. And I noticed that this part of the Lagrangian, if I didn't have C mu I, would have had negative norm states, because it's like something light-like in some internal directions, del x minus del x plus. But there's a shift symmetry where I shift C and I shift X minus, and that shift symmetry makes sure that this term doesn't introduce new negative norm states. And at the end of this procedure, I've got exactly the Lorentzian 3 algebra theory that was discovered by these people. Actually, the second version, these people wrote down the second version which had this gauging, which makes it manifestly positive definite. So what have we learned? We've learned that by taking n equals 8 Yang-Mills, you can actually rewrite it in a language which knows about 3 algebra interactions, albeit Lorentzian 3 algebra interactions. Now that's rather intriguing, and as I said, we've got the theory with all symmetries in place, but unfortunately the superconformal invariance and the SO8 invariance are simultaneously broken as soon as I give a wave to x plus I, replace it by its constant value g Yang-Mills, and then the theory reduces to n equals 8 super Yang-Mills with a coupling that's the mod of this vector. Now this looks like a disappointing conclusion, but we should remember that if I can find a way to take this theory and take the wave x plus I to infinity, if I could just choose the wave infinity, which I can't because infinity isn't a number, then I would in fact have the theory that that everyone's been trying to look for with all of its symmetries in place. Okay. Now I admit that no one knows how to do that, but that isn't a guarantee that it can't be done. Now I'd like to close in the last 2 minutes by discussing a new thing about these Lorentzian 3 algebras that I've just derived from Yang-Mills. And the question is the following. This non-abelian duality, this DNS transform we used, would it work if I started with Yang-Mills that also had alpha prime corrections built into it? Now we certainly know how to do that in the abelian case, where it's not Yang-Mills, it's just the DBI, Maxwell DBI of ordinary single D2 brane. And we know in that case, due to these people's work many years ago, that you can perform an analogous duality and replace the gauge field by a scalar, and then that scalar is interpreted as the M direction. And we also know from these people's work that this can be supersymmetrized nicely. So there's an entire fermionic DBI that's known. Now the thing that we did was to ask what about the non-abelian case, which brings up completely new issues, because it's only in the non-abelian case that you have commutators in Yang-Mills and you have triple commutators or triple brackets in the 3 algebra structure. So the question was, does the 3 algebra structure survive alpha prime corrections? And of course, Neil already mentioned this in response to a question. You can't think of doing anything in this subject to all orders in alpha prime, because even for Yang-Mills, we don't know the non-abelian DBI to all orders in alpha prime. So the best you can do is start with the first non-trivial order, and that's what we did. So here it is. So let's take n equals 8 supersymmetric Yang-Mills in 2 plus 1 dimensions, and let's add all the corrections of first non-trivial order in everything. So these are the field strength to the fourth. These are f squared, d squared terms. There are some ff commutator terms, xij is xi comma xj. There are these terms, and if you thought that was all, there are also these terms. So this is the entire corrected, alpha prime corrected super Yang-Mills. And the key point here is it contains a dynamical gauge field, non-abelian gauge field in F. And all the x's are 7 in number because this is Yang-Mills, and small I goes from 1 to 7. Okay. So what we've been able to show is that that whole thing is dual to this B wedge F Chern-Simons plus these kinetic terms for x plus all these terms. And notice that these terms involve the d hat derivative on x, which I defined earlier, which is the Lorentzian 3 algebra derivative, as well as they involve xijk, the 3 product, x plus into xi, x plus I into xj comma xk. And after you've added up all this, there's also a potential, which will go to the next page. So this I've already defined, and the potential is here. Now I think this is the nicest part, because you see that the potential, which was sextic in the alpha prime going to 0 limit and made a conformal theory, has now been corrected by all these terms, which are 12th order in the field x, but all of them appear in the 3 algebra format where xijk is this kind of thing. So this, I feel, is an encouraging sign that this theory is a rewriting of D2 brane Yang-Mills that will work to all orders in alpha prime or in L Planck. And I just want to stress one thing before I close, that this is not something which would happen for any old Lagrangian reduced from 10 dimensions. The relative coefficients of the 10-dimensional terms are very important, and only if they're exactly right does this miracle happen. Good. So these are the conclusions of this part of my talk. And and we conjecture that this theory, if you dualize in this way, has an SO8 enhancement to all orders in alpha prime. Good. So summary of my talk is that while we've made much progress towards finding the multiple membrane field theory, we don't seem to be there yet, and it would be premature to give up on any one of the many candidates around, which anyway are all related. They're all three algebras. Deconstruction is the only way we know how to relate membranes to D2 branes in the large K limit, but we would like to understand compactification, for example, by taking a stack of M2 branes and then compactifying a transverse direction, as has been done for D2 branes, but we are nowhere near knowing how to do that. And this is one little observation, that you can dualize the D2 brane into a completely superconformal SO8 invariant structure, and the three algebra structure is preserved by alpha prime corrections, but spontaneously broken by giving a wave. So with that, I will end and leave you with one small thought. Thank you.
Thank you very much. Questions?